move to a theorem that kind of gives a characterization of definition of a value being eigenvalue of a given matrix actually. Okay? So the theorem goes like this, that imagine you have an n by n matrix and lambda is a complex number, then following these statements are equivalent actually. Okay? It kind of provides the characterization of this, the characterization of lambda being eigenvalue. So the first lambda is eigenvalue of A, that's number one. Second is that AX equal to lambda x for some x in Cn. Okay. Third is that A minus lambda I operated onto x, okay, has a non-trivial solution. Okay, so it has a non-trivial solution. That's the fourth characterization. A minus lambda I is invertible. Is not invertible. Is not invertible. And the fifth is that A transpose minus lambda I is also not invertible. Okay? And really the sixth characterization is that if the lambda is eigenvalue of A, lambda is eigenvalue of A transpose as well. Okay? So these are some of the characterizations of lambda being eigenvalue of A. So in other words, if you want to prove, for example, that lambda is an eigenvalue of a matrix A, so either you prove this, or you show that this system has a non-trivial solution, or you show that the operator A minus lambda I is not invertible, or you show that A transpose minus lambda I is not invertible, or you can also show that lambda is an eigenvalue of A transpose actually. So all of these statements are equivalent actually. So what is the proof of it? One if and only if two. This is really definition actually. So you don't need to prove it. Okay, so one if and only if two is really definition. Two if and only if three. Okay, two if and only if three is really the rearrangement of the same statement actually. So when you say that Ax equal to lambda x, then you know, so in other words, when I'm saying that Ax is equal to lambda x, this is true if and only if, you know, Ax minus lambda x is 0, if and only if A minus lambda I operated onto x is 0 actually. Okay? So, I mean, if there is an x, okay, so if there exists an x, okay, such that in Cn such that Ax equal to lambda x, this is true if and only if there exists x such that, so there exists x such that Ax minus lambda x is 0, and if and only if there exists x such that A minus lambda x equal to 0, and this means that this A minus lambda x equal to 0 has a non-trivial solution actually. So this is really the restatement of the if statement number 2 actually. So 2 and 3 are equivalent. 3 and 4, why the 3 and 4 are equivalent? Okay. Why the 3 and 4 are equivalent? For 3 and 4, I would like to basically say that if, so this is for example a result actually, that for a say a linear transformation on a finite dimensional vector space, or from one finite dimensional vector space to another finite dimensional vector space. So if you have the kernel of a linear transformation, okay, where the T is a linear transformation from, say, one finite dimensional space to another finite dimensional space. So we know that this T is going to be 0. In other words, this T is going to be 1, 1 if and only if the range of T. So if T is a linear transformation from a space, finite dimensional space V to W, okay, and then the kernel of T is trivial if and only if the range of T equal to the entire space, what do you call, W. That is T is 1, 1 if and only if T is onto, okay, or T is 1, 1 if and only if T is invertible. T is invertible. So corresponding to this, I can say, okay, so the corresponding to this, I can say that if I consider this T as a matrix, for example, A minus lambda I, okay, A minus lambda I, then what would be the meaning of A minus lambda I x equal to 0? The meaning of this is going to be that the null space, or for example, if this T is a linear transformation that is 1, 1 if and only if T is invertible, you can also say that if the null of the matrix corresponding to this linear transformation T is trivial if and only if A is invertible. Okay? So I'm saying that recall this result. So this is a recall that for a given linear transformation, kernel is trivial if and only if T is invertible. But if if this is true, then this is also true, that if the null of some matrix is not trivial, then A is not invertible. Then that matrix A is not invertible. Okay? Now think about what does this statement 3 is telling you. 3 is telling you, so this is a general fact. 3 is telling you that the null of A minus lambda I is not 0. This is not 0. So if this is not 0, this will be true if and only if A minus lambda I is not invertible. This is not invertible actually. Okay? So this is not invertible. So that's what precisely you need to show. That since this has a non-trivial solution, that means that the null space of A minus lambda I is non-trivial, and therefore A minus lambda I is not invertible. And if A minus lambda I is not invertible, the null space of A minus lambda I is not 0, and therefore, you know, there exists a non-trivial solution. So this follows from basically this general observation. Okay? 3 and 4. Why 4 and 5 follows? 4 if and only if 5 follows. This follows from the fact that if A is invertible, a matrix A is invertible if and only if A transpose is invertible. Okay? A matrix A is invertible if and only if A transpose is invertible. Now what is, so you can say A minus lambda I is, and hence A is not invertible if and only if A transpose is not invertible actually. So I'm going to say A minus lambda I is not invertible. Okay? This is not invertible if and only if its transpose A minus lambda I transpose, which would be equal to A transpose minus lambda I transpose. So the I is an identity, it's a symmetric matrix, so it would stay same. In other words, A transpose minus lambda I is not invertible. Okay, so this is not invertible. So this shows that 4 and 5 are equivalent. Why 5 and 6 are equivalent? They are equivalent because 1 and 4 are equivalent actually. Okay, since for any given matrix, if A minus lambda I is not invertible, then lambda is an eigenvalue of that matrix actually, no matter what matrix you have. Now I know that A transpose minus lambda I is not invertible. So by equivalence of 1 and 4, it follows that the lambda is an eigenvalue of the matrix A transpose. And if the lambda is the eigenvalue of the matrix A transpose, then A transpose minus lambda I is not invertible. So this is also true from 1 and 4. Okay? So the proof is not difficult. Proof is pretty much straightforward. It's based on the previous facts that you know. But something that is important that you get from this theorem is that there are several ways to say that lambda is an eigenvalue of the matrix A. At least you saw the 5 other methods to say that the lambda is an eigenvalue of the matrix A actually. So if any one of them is true, lambda is an eigenvalue of the matrix A. Okay? So now let's move to our first question. Does every matrix has an eigenvalue? Okay? So this is the first question we would like to address. Does every matrix has an eigenvalue? And the answer is yes actually. And we will prove this result, or we will try to answer this question in the form of what do you call two lemmas and then a corollary actually. Okay? So the first question, every square matrix, every square matrix has an eigenvalue. Okay, so this is what that we will like to mainly show. Okay. Now we know that if you have, for example, given a polynomial, say p of x, that is really say x squared plus x plus 1, and then we know that if in this polynomial, if I put a matrix A, so this would be P of A is going to be a matrix that is going to be A square plus A plus identity matrix, what do you call A actually. Okay? It's going to be the identity matrix, it's going to be A. For example, if I take say a matrix A, okay, which is 0, minus 1, 1 and 0, then what we can show is that this matrix is, the square of this matrix is minus I actually. Okay, so I2, this second order 2 by 2 identity matrix. So what does this show? That A squared plus I is a 0 matrix. So I can say that this matrix A annihilates, I can't say that it's a root of the polynomial, say P of x equal to x squared plus 1, but I'm going to say that if in the polynomial you substitute say P of x equal to x squared, if you substitute the matrix A, so what you're going to get, okay, the P of A is then going to be, what do you call, A squared plus identity, which is going to be the 0 matrix of, you're going to say that this matrix A annihilates the polynomial, what do you call, the matrix A actually, or you can also say that the polynomial annihilates the matrix A, or other way around. Okay, so here is Here's a little definition. So the definition goes like this, that if A is a square matrix and P is some polynomial, P is P of x is a polynomial, it could be a complex polynomial. Okay, it's a polynomial such that if in this polynomial you substitute A, you get 0, then we say that this polynomial P annihilates the matrix A. P annihilates, okay, the matrix A actually. Okay, so by annihilation in Urdu you call it tabahi actually. So it just, swallows, the matrix A and spits out what you call 0. In other words, it spits out nothing actually. Okay, so this is what the definition of A. I would like to then prove an important lemma, one of the two important lemmas that answer, for example, this question. So what does this say? So it says that if you have a matrix A, that is a square matrix, then you can find a polynomial P, then there is a polynomial, okay, polynomial P of degree at most n square, okay, so where n is the dimension of the matrix A. So there is a polynomial of at most degree n square that annihilates, okay, that annihilates the matrix A, okay, that annihilates the matrix A. And if A has real entries, so if A has real entries, then the polynomial is going to have real coefficients actually. Okay, so this is also an important thing. So here's the proof of this result. So what does this result is telling you? For every matrix, there is a polynomial of degree n square, or at most n square, or degree less than or equal to n square, that annihilates the matrix A actually. Okay, in other words, if you substitute A into that polynomial, you're gonna get what do you call 0. Okay. Now, why this is the case? The vector space. So let's just start with the vector space. This is space M and F actually. Okay. What is the dimension of this matrix M and F? Okay. The space M and F, the space M and F has dimension at most n square. Okay, so this has dimension n square, actually not at most, but dimension n square. For example, if you take M2, in other words, you take 2 by 2 matrices, you take say A, B, C, D. So, which matrices are in the basis of this matrix, this M2, which matrices form the basis of it. Then the basis of M2, so one of the bases of M2 is this 1, 0, 0, 0, 0, 1, 0, 0, and 0, 0, 1, 0, and 0, 0, 0, 1 actually. Okay. So there are 4 matrices which annihilate, which are the basis of M2. So if you're going to have n by n matrices, so how many such matrices are going to create the basis of Mn? So they are going to be Mn square actually. So therefore the dimension of Mnf is really, what do you call, Mn n square actually. Okay, n square. Then, if you take, for example, any matrix, then if you take, for example, matrices that are n square plus 1, one more than what do you call the dimension of MNF. So if I take matrices that are, one more than what do you call Mn, the dimension of MNF, then these n square plus 1 matrices must be linearly dependent actually. So in other words, if you have a three-dimensional vector space, okay, R3, so in R3 if you take 4 vectors, okay, or 5 vectors, then those 4 vectors must be linearly dependent actually. So one of the vector must depend on the other 3 vectors actually, okay, so they must be linearly dependent. So if the dimension of, say, space MNF is n square, then these n square plus 1 matrices, which are these matrices, say I, A square up to A power, say, n square, okay, A power n square. So how many are these matrices? So these are n square matrices plus 1 are linearly dependent. All of these are elements in MNF and its dimension. So these are like vectors in MNF. So these are like n square, so what is the dimension? N square. So these matrices must be linearly dependent actually, okay, so they must be linearly dependent. That is, if you make a linear combination of these, so if you make a linear combination of these, C0I plus C1A plus so on and so forth, and say Cn square, An square, okay, and you equate it to 0, okay, then there must be some Ci's, okay, some Ci's which are non-zero, okay, which are non-zero. So now some Ci's must be non-zero. Now, or at least one of the matrix would be depending on other matrices actually. So if you equate them to 0, some of the constants are going to be non-zero, or at least one is going to be, at least one of the term you should be able to express in the terms of the others actually, okay, because you are taking more vectors than the dimension of this space, okay, so this is a basic fact. So if I take, for example, R as the maximum of the index, okay, R is the maximum of the index between 1 and n square, such that the coefficient corresponding to it is not 0, okay. So if R is the biggest index, from 1 to 0 is n square, such that, corresponding to this index the coefficient is non-zero, then what does it mean? It means k is between 1 to n square and ck is non-zero. This means that this matrix is non-zero. C0I plus C1A plus, okay, then you're going to say that CR is not 0 and C0I plus C1A plus so on and so forth, CR A power R is equal to 0. Okay, so they are so this combination is 0, but the coefficients are what you call the CR is not 0. So if this is the case, this shows that you got a non-constant polynomial, say P of x, which is C0 plus C1x plus so on and so forth, CR x power R, that annihilates, so above statement shows that the polynomial, so if you take this polynomial, then this polynomial annihilates the matrix A actually. Okay? And R, okay, it could be a number up to what do you call n square. So this proves the lemma. Okay, so what does this prove the lemma? That if A is an n by n matrix, then there is a polynomial of degree, for example, R, that degree is at most n square, and that annihilates A actually. Okay, so this annihilating polynomial comes from the factor that if you take, for example, n square plus 1 matrices, they must be linearly dependent, and hence, you know, such a polynomial is really guaranteed actually. Okay, so example, and then the second important lemma, and if we're going to combine these both lemmas, then we are done. Okay, then we are done. So if A is a matrix that is like A, B, C, D, okay, any 2 by 2 matrix. So for this 2 by 2 matrix, can I find an annihilating polynomial? I can follow the same procedure. I can say that, okay, take matrices I, A square, A cube, and A power 4 actually. Okay? And say compute A square. Compute A square. So if you're going to compute A square, you're going to get a matrix, I'm directly writing it, A square plus BC, B times of A plus D, okay, and C times of A plus D, and BC minus AD. So this is what that you're going to get when you compute the A square. So from this A square, now I can guess actually that if from this A square, if I take, for example, A plus D, okay, if I take, for example, A plus D and say multiply by A, okay, so if I take matrix A square, which is this, and I multiply this with A plus D, so this will become BA plus D, CA plus D, and A times A plus D and D times A plus D, and I subtract it, then these two terms will vanish actually. Okay, these two terms will vanish. And the matrix that you're going to get finally is going to be the matrix that is BC minus AD 0, okay, and 0 BC minus AD. So this is what that you're going to get actually. Okay. So from this I can guess actually that if I take A square minus A plus DA, and this is like BC minus AD multiplied by identity matrix. So BC minus AD multiplied by identity matrix, if I take this, this is equal to 0. This is equal to 0. But if you see what is this number is really the trace of the matrix A, and this BC minus AD, so the BC minus AD is really the determinant of the matrix A actually. So I can say that for any given 2 by 2 matrix, so if you have a given 2 by 2 matrix, the polynomial that annihilates this given 2 by 2 matrix is the polynomial which is x square minus trace of the matrix A multiplied by x and plus AD minus BC multiplied with the identity matrix A actually. Okay? So here we do AD minus BC, this will go. Okay? Multiplied by the identity matrix A actually. If you bring them on other side, it's going to become AD minus BC. Okay? So for any 2 by 2 matrix, this is, this AD minus BT, you can also call it the determinant of the matrix A. So for 2 by 2 matrix, this is an annihilating polynomial.